So now we're going to talk about stress transformations. And so the idea here is that if you're given a stress tensor in one coordinate system, this is a way to express it in another coordinate system. Okay, so the key thing sort of to keep in mind is you have to think about the rotation required to align the original coordinate system with the desired coordinate system. That's the rotation that you're looking for. Okay, so for example, if your original coordinate system is this, and your desired, so this is the original, and then your desired is this, what's that rotation that you're doing? You're rotating, so that x-axis is going from here to here, right? Mm-hmm. So that's a 90-degree rotation. It's happening about something parallel to z, okay? But notice that that's, if it was a positive rotation about z, according to the right-hand rule, it would go the opposite way. So this is a negative 90-degree rotation about the z-axis. You see that?
So you can still just use the long degree.
Yeah, you could, yep. You could, right, you could call it positive 270, yes.
So when it's counterclockwise, or when it's clockwise, same rule as like it's rotating.
Yeah, except now it's 3D, so you have to think a little bit about what clockwise and counterclockwise mean. But if you're,
Wait, how do you mean?
if you're looking with the coordinate system.
Well, like whatever you're rotating about.
Yeah. So yeah, if you're looking with that axis pointing towards you, then counterclockwise is positive and clockwise is negative.
Okay.
But you know what I'm saying about like.
Right, like you're just imagining like, so if you're rotating about x, it would be like this way would be negative and that would be positive?
Yeah. Yeah, just always imagine that the coordinate system is pointing towards your eyes, and then it's counterclockwise, clockwise. Okay, so this is a negative 90-degree rotation about z, or you could also do positive 270 about z. Okay, so given that definition of the angle that you're rotating this thing, so once you know the angle and axis to rotate about, a rotation of theta about the x-axis has a rotation matrix Q like this: 1, 0, 0, 0 cosine theta, sine theta, 0 negative sine theta, cosine theta. A rotation theta about the y-axis well, y always has to be a little bit difficult in some way. So you'll see the similarity in the pattern, but there's a switch in the signs. This is cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, bless you, 0 cosine theta. And then a rotation of theta about the z-axis. This rotation matrix Q is equal to cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1.
For like, the X one, going from like X to Y, it's like you run the shift down one row and then
Yeah.
it's like you're not doing it. If it's like the cosine,
Yeah, I guess that's sort of, I wonder if it really does that. I'm not going to think about that. I'm not going to think about it that way, if that's okay. Like Pac-Man.
I was trying to figure out, like, there's got to be something that's doing that.
I think of it as like this. It's like the pattern is like X and Z, you know? You have the zeros and ones in the axis you're rotating about. Cosine, sine, negative sine, cosine. And then Y just always has to be weird because of its right-hand rule thing. Okay, so let's see an example of this with vectors. Well, how does it work? That's you. Sounding all stupid. Okay, so let's say we have this vector. It has a length of 10 and makes an angle of 30 degrees. Okay. And in this coordinate system, we know that this is going to be 10 times cosine of 30, 10 times sine of 30. So this comes out to be 8.6650. And now let's say we want to express that vector in a new coordinate system where, so it's still the same vector, but now we want the x-axis to be aligned with it. Well, it's pretty easy to figure out, you know, if it has a length of 10 still, it's still the same vector, then that's just going to come out to be 10 for x, 0 for y, 0 for z, right? Mm-hmm. But so let's see that with the, happen with the matrices. Okay, so it should give 10, 0, 0. Okay, so let's think about the rotation of the coordinate system. So if you want to go from a coordinate system like this to a coordinate system like this, what rotation is required?
30 degrees positive.
Positive 30 degrees about the z-axis.
Yes.
Yep. And so our rotation matrix is going to be cosine 30, sine 30, 0, negative sine 30, cosine 30, 0, 0, 0, 1. And so that comes out to be 0.866, 0.50, negative 0.5, 0.866, 0, 0, 0, 1. And now multiply that matrix by the coordinates, the components in the original coordinate system. Okay, so so it's this times 0.866, 0.50, and you get, if you multiply these two together, you get what we knew we should get, 100. 0.866 squared is 0.75.
Point for 8.675.
Yeah, it was 8.6675.
The vector was.
Oh, yeah. Thank you.
Okay.
So 10. I'm sorry. Yes, that's better.
I had a question.
Yeah.
Let's say you wanted to like do multiple rotations, like let's say rotate 30 degrees, then like 50 and another.
Yeah.
Would you just chain the matrices?
Yeah, you have to be careful because you can do it, but you have to be careful because once you've done one rotation, now your other two axes are not what they were before. So if you think like I want to rotate it this way and then rotate about my old y-axis, it takes some thinking to do that kind of stuff. This is kind of not necessary for this class, but this is a useful, I think, way to think about it. So if you start with a vector in coordinate system A, and you want to express that vector in coordinate system B, so that's what we're talking about. So to express I'm going to call it an A vector. This is the original coordinate system. In B, This is the desired coordinate system. The columns of the rotation matrix are the A coordinate axes expressed in the B coordinate system. And this works for any rotation, any crazy rotation. Doesn't have to be about X, Y, or Z. Like, let's see it work in the example we just did. So this is our A coordinate system, this is our B coordinate system. The columns of the rotation matrix need to be these coordinate axes expressed in this coordinate system. Okay, so the first column is this x-axis expressed in this coordinate system. It's going to be 0.866, negative 0.50. The second column is this y-axis expressed in this coordinate system. It's going to be positive 0.5 in x. If you can visualize that here. Positive 0.5 in x, positive 0.866 y, 0. And then the z coordinate, the z-axis doesn't change because we're rotating about that, so that's just 0, 0, 1.
So it's like imagining the axes as vectors?
Yes. Yeah. You don't have to think like that in this class, but if you, I don't know, there are times when it comes in handy. Okay, so now that we have that, you can use these same rotation matrices to express stress tensors in new coordinate systems. And so you define the rotation matrix the same way based on how you're rotating the coordinate system, but now your new stress tensor is going to be the rotation matrix times the stress tensor in the old coordinate system times the transpose of the rotation matrix. Okay, so loosely thinking, why do you need two of these? To represent a vector in a new coordinate system, you only had to multiply by a single rotation matrix. You can think of this as one rotation matrix rotates the faces of the stress cube. And the second matrix re-expresses those tractions in the new coordinate system.
Which does which?
Let me think for a second. the Q transpose is the one that what you're basically doing is, remember the rule where to get the traction on a face, you multiply an outward facing normal to the stress tensor. So these two on the right are basically in turn taking each of those outward facing normals and multiplying them by the stress tensor. Okay, so this is just coming up with tractions in the rotated thing,
Okay.
but those tractions are still expressed in the old coordinate system, and now this expresses them in the new coordinate system.
Thank you.
Is there a grouping that matters here or not?
Nope, grouping never matters in matrix multiplication.
But order does.
Order does, yes, exactly. One thing that's interesting about this, somebody asked me about, there was something about transpose versus inverse before. I guess it was when we were talking about the compliance matrix. Notice that a rotation matrix is an orthogonal matrix. So rotation matrices are orthogonal. Which means that the columns of the matrix are perpendicular to each other. The columns are mutually perpendicular. Orthogonal matrices, let me say 4 orthogonal matrices the inverse is the transpose. That's the only type of matrix where you can assume that that's true.
Just bring it back to help.
Yeah, well, I'm happy for you. It's nice to revisit Calc 4 whenever you can.
It comes up everywhere.
Yeah.
I know, I wish if they had you take that as like earlier on.
Oh, yeah.
I just like how it's like,
Uh-huh.
it'd be helpful.
Okay, well, let's do a couple things. So let's say we have a stress cube. And let's transform this stress so if this is the original coordinate system, let's rotate it (45 degrees) that way. So this is X, this is Y, this is Z. Okay, so notice that in our original coordinate system, all we have is normal stresses, okay? We have a tension along the x-axis, compression along the y and z axes. What do you think is going to happen when we do this rotation? I think it's easy to sort of think like, okay, these normal stresses and shear stresses are kind of fundamentally different things. But what I want you to notice is when we do this stress transformation, we're going to go from something that only has normal stresses to something that has normal and shear stresses. Okay? What?
If all of the, would you be able to represent then any object in the coordinate system where they would all be like that, or is it just a specific,
Oh, that's such a good question. It turns out that every stress, any stress state you can come up with, somewhere there's an orientation of a coordinate system where there's nothing but normal stresses.
That's cool, that's so cool.
It's super useful. That's what principal stresses are. And it gives you a way to sort of, without those principal stresses, it would be really hard to come up with a way to determine, like to compare how close this material is to breaking. And so principal stresses are going to be really important.
Sounds like art exhibits where you like walk and you orient and then it like finally gets like whatever.
Yeah, oh yeah. Right, yes.
And then all of a sudden you go a little further and then it's way.
You're in a very philosophical mood today. Okay, it's a nice calculator. It takes a while to get used to, but I feel like it has a longer learning curve than the other ones, kind of, but
I'm upset about.
Well, that one has like a built-in mouse.
yeah. Okay, so let me just go through how to do this so everyone's on the same page. So,
Like A, B, C, D, you should be able to like turn aside and then turn to the keyboard.
so this rotation is going to be positive 45 degrees about z.
Wait, that's super much more curves than mine.
Okay. And so that matrix is going to be
That's what it's
0.7071, 0.70710. And then negative 0.7071, 0.70710, 001. On a calculator, so on an 84 calculator or an 83, you have to go into the matrix thing and edit your matrix. On an 89, you could, do something like this.
Do you know what determines whether the windows are open or not?
No, do you like them open better? I'm sure there's a button somewhere. You
I'm,
do?
like, staring at the people as they walk by.
I shut the window so people wouldn't know that the TI Inspire rep is back.
You have a reputation around
Kind
here.
of like blinders on yours.
Yeah, exactly. Well, so on a TI-89, you could enter it like this.
Those big books makes me like less able to concentrate.
Huh.
I like them now.
It,
I like light.
it's like kind of like it's like
This room sucks out. It's like,
it's like the same. It's just like being
It's like the bunker opening.
It's like really like rocks.
Like resin back here. When you finally leave, the waterfall is just
Yeah.
I wonder how much money it does cost just to have a person.
Yeah.
Does that
Right.
It's that cost. It's cool.
Yeah.
I like
Okay, just bear with me for 2 more minutes. So now you can go like, just take Q times however you have your stress tensor defined. On an 89, you could do it as like 20, 0, 0, 0, negative 10, 0, 0, 0, negative 15. Then multiply by Q, hit the transpose button. Did everyone find that transpose function? Okay. And it'll give you an answer of 5. Negative 15, 0. Negative 15, 5, 0, 0, 0, negative 15.
Question?
Yeah.
Is any given traction the same based on either your old tensor or new tensor?
Any given traction. Yeah, I mean, yes. If you, so say that now you wanted to calculate the traction on this face. You know, with an outward normal like that. You could use the original stress tensor and multiply it by 0, 1, 0. That would be the outward facing normal, right? Or you could use the new stress tensor and multiply it by what would be in this case, I guess, 40, it would be 0.7071, 0.70710, like cosine and sine of 45. Even though the numbers are different in the two coordinate systems, that would define the same vector, the same outward facing normal vector, and it would give you the same traction. Yep. So all that stuff, I mean, these two stress tensors mean the exact same thing. Anything one can give you, the other one can give you. It's just you have a different, basically what you've done is reorient the cube, you know.
Kyle, I noticed some of the hard prompts said like draw the cube. Could we do that here? After you wrote
Yeah, you know, actually, I meant to get rid of those problems because it's so hard to draw three-dimensional stuff. This one wouldn't be too hard though. So this would say,
I just want to like visualize
yeah,
what it looks like.
let's, okay, so now the new cube would look something like, well, let me just draw it like straight on. So now this is the positive x face.
Yep. We're
This-
looking at the z face.
Yep, we're looking at the z face. And so this would be 5 megapascals that way, 15 that way, which also means this is 15, and also means this is 15, and this is 15. And then on y, we also have positive 5. And then on the z face, it's going into the face 15. So yeah, I do think it's useful to visualize stuff like that, but it's just so hard to draw. I don't really ever ask that question anymore. It's not hard to draw if you draw it straight on like that. It's just like trying to draw the 3D projections and stuff, you know. Anybody have any other questions?
Yeah, so if we want to do this on an off-axis rotation, it just gets real complicated. Like instead of
So if you wanted to rotate about something that wasn't one of the coordinate axes, you would probably just want to try to figure out how to do it using the fact that the columns of the rotation matrix are the A coordinate axes expressed in the B coordinate system. It gets easier to do it to think of it that way.
Okay, would it be possible to do it like, at most you need 2 rotations, one this way?
Yes, and you can do that, but you have to be careful. Maybe I'll think about whether it's worth doing an example like that. I used to do a lot of that kind of stuff in a job I used to do. Trying to represent sort of funny rotations, like rotate this way, and now you have to rotate about this other thing to come up with this final thing. But it definitely gets more complicated than you would think. It's not as much as just like multiplying by this matrix, then this matrix, then this matrix, it's more subtle than that. Any other questions? Okay. That's it. Have a good weekend. I have a meeting at 12, so anybody who's gonna come to office hours, I'm not gonna be there till 1 today. All right.